using these problems, I'm going to be able to show you a couple of tricks that you can do when working with Seth that are generally useful for other problems too. So that's another reason. And the third is like the concept of that has been very important in fine-grained complexity is that when you work on a problem and you try to show a lower bound, just finding the right starting point is like more than half of the work. Like whether you have to reduce from OV or from negative triangle or from threesome and so on. And that's gonna matter here. Okay, so what are we talking about? So dynamic graph algorithms. So it's like you have a graph, but it changes with time, and you want to maintain it. So there are updates that change the graph. Then there are queries that ask something about the graph, and whenever there's a query, you have to answer something about the graph. And you want to do these things fast. Okay, so we have a graph, and we can pre-process it before like the updates start. So there's some pre-processing stage, and then there are edge updates. So we add an edge or delete an edge. That's like the updates we will think about. And there is query that asks something. Like it depends on the problem. It could ask for the maximum matching. It could ask for a shortest path. It could ask for reachability or anything. And the general goal is to minimize the time, like the pre-processing time to be as efficient as possible, the update time and the query time to be as small as possible. And like the gold standard is that, well, the pre-processing is just linear time, like in the size of the graph. And then every time there's an update, you spend constant or polylog time. You don't, there's one edge that got changed. You don't go and recompute everything about the whole graph. So you don't spend linear time in n. You spend like sublinear time or polylog time. And the same with the query. Like the query should be like constant. You just know the answer all the time. But polylog is fine. And when you have this kind of thing with, there's like worst case time where, every update needs to spend only polylog time. But then there's also amortized in this topic. Like maybe some updates will be expensive, but overall it's good and so on, or maybe the total and so on. Like these distinctions will not really matter for us because we will talk about lower bounds. And the lower bounds we will show will even talk about amortized and total, so there will be like as strong as possible. But when you talk about upper bounds, sometimes there's upper bound that's only amortized, but not as good, worst case, and so on. So here's a okay, the first example of a problem, and this is probably one of the most famous problems in this topic, connectivity. So you have a graph, you have edge updates, edges come and go, and the query asks, are two nodes connected? Or is the graph connected? Or like, and it's an undirected graph, so it's like, are they in the same component or not? So the trivial algorithm, for most of the problems we will talk about, the trivial algorithm is linear. So like connectivity, if I just give you a graph and I ask you, are two nodes connected, you can just run BFS or DFS or whatever. It's very easy to solve this problem in linear time. So the trivial algorithm for the dynamic problem is whenever you have an update, you just run DFS from scratch. So O of m time per update. Or alternatively, you can like not do anything when there's an update, and then when you get a query, you can just run the DFS then. So you could also do O of m per query and constant per update. But there's some famous results, the 90s, that give a polylog time for the updates and the queries for this problem. So you can only spend like, people have been improving the polylog, but the point is like it's very fast to maintain. Some link cut trees and some fancy stuff and so on. And so that's great. It's one of the success stories of that field. And there are like matching lower bounds in the cell probe model. So it's like an unconditional lower bound statement. It says that any algorithm needs to access the memory in at least log n places in order to solve this problem. And there's a lot of such lower bounds. And sometimes they can be very close. Like this is a very almost tight lower bound. But this is only when, when the problem has become So these lower bounds, they are stuck at log squared. So there is no unconditional lower bound in this model higher than log squared for any of the problems we care about. So this like lower bound machinery is very relevant for problems that we already know are kind of easy, that we already have the polylog n updates, then that's great. But then if you look at a bit more difficult problems, there are huge gaps. So specifically, look at the same problem, but now in directed graphs. So now instead of connectivity, it's reachability. So again, you have a graph, the edges come and go. And let's say ST reachability, you get 2 nodes as a query, and you ask, is there a path from S to T? So it's no longer just like figuring out if they're in the same component or not. You have to check if there's a path. And another version is like single source reachability. So specifically in this talk, I will look at the problem where you have to return the number of reachable nodes from a source. This number SSR. So you get, there's a source S, it's a fixed source, and the query asks how many nodes can this source reach in the graph. So it's some number from 1 to n or 0 to n. And so, but again, there are the trivial algorithms. So linear is still trivial. Every time there's an update, you can run from your source, you can run some BFS or something, and you get the answer or whatever. And this is like the best known, essentially. If the graph is very dense, you can use this, some fast matrix multiplication algorithm that is a bit better in the dense case. But in the sparse case, there's nothing non-trivial that we know. And unconditional lower bounds are still at log n, so there's a huge gap. Okay, and there's this is just a list of fundamental problems that you could ask the same question about. Mm-hmm.
Find these joint sets algorithms useful toward this problem?
Yeah, union find is useful, but for undirected graphs, but not for directed. Yeah. It's also, I think it's only like when you add edges, not when you delete. So it's not doesn't solve the problem, but it's relevant. Yes. And yeah, so we would like to know which of these are easy, which are hard. Easy in the sense that we can solve it with polylog and updates. Or not. And notice, like, in fine-grained complexity in the static, not dynamic setting, we don't. Most of these problems are not even relevant for us because they are linear time problems. Like reachability, single source reachability, it's a linear time problem. So we're not going to prove lower bounds for it because it's done. But now in the dynamic case, it's suddenly interesting. Like two linear time problems like connectivity and reachability. When you think about the dynamic, whether you change one edge, do you have to recompute everything from scratch? Then there could be a gap. One of them could be in polylog, and one could be linear time per update. So it's like, we haven't looked at these problems in the other model. But in dynamic, we can study them, and it's interesting. OK, so here's some things we know. So connectivity, as I said, is easy, and turns out that these other problems are also easy, and I'm not going to talk about the algorithms, but so we had algorithms for them that are pretty fast. And then for diameter, I claim that it's hard. Like we don't expect to get polylog n updates. Can anyone explain why? Yeah, so earlier we saw this quadratic lower bound where the graph had n edges. So what that means is, so if a problem is not linear time, just static, then there's no way that the dynamic could be that fast. Because then you could say, OK, I have this graph. I want to solve the problem on that graph. I can use a dynamic algorithm. I just start with an empty graph, and I add all my edges. I'm adding, like, let's say, m edges. And then I ask a query, and I get the answer. If I had this green status, like the gold standard, every update cost only polylog, query cost polylog, preprocessing was fast, then the whole process only took linear time, or near linear time. And then I could solve my problem in near linear time. So what this means is that if we have a superlinear lower bound, then we also know that the problem is not super easy. And that's good. For diameter it's good, but for all the other problems, it will not say anything because we don't have linear time algorithms for that. So there was a paper, a very influential paper by Mihai Petrashku, which proved lower bounds under threesome. So now we're talking conditional lower bounds, fine-grained lower bounds for these dynamic problems. And in fact, this is the paper that introduced like this additive hashing into threesome, which Nick talked about, like the reduction from threesome to convolution threesome was in that paper, and then the reduction to triangle listing, which he used then to get lower bounds to dynamic problems. But these lower bounds were very weak. Like they were polynomials, so they show that these problems are not easy, but they're very far from being tight. And then later we had a paper where we started not from threesome, but from like other conjectures, Seth, APSP, and so on. And we showed the tight lower bounds for a lot of problems. So I'm going to tell you like some of the results from this paper. And the conceptual thing we did with that paper was to say, like, we have these conjectures in fine-grained complexity. Let's try to use them to explain like this in this topic in dynamic. Let's not restrict ourselves to threesome. Let's use any conjecture and see what we can get. And it turns out, for each problem, if you use the right conjecture, you can get the tight bounds. OK, so here's a theorem that I want to prove now. For reachability, single source reachability, this counting problem, I claim that you cannot get anything non-trivial. So in sparse graphs, there's a linear lower bound. The trivial algorithm is optimal, assuming Seth. So this is the plan for the reduction. So we're going to reduce orthogonal vectors to this dynamic problem. So it's now like this is a twist, like reducing a static problem to a dynamic problem, and it's going to be fun. Okay, so we start with orthogonal vectors. We have these two sets of n vectors, and they have some dimension d. That's pretty small. And we want to know if there's an orthogonal pair. So here's a reminder of V. A pair is orthogonal if there's no coordinate where they're both 1. So the plan is to create a graph, dynamic graph, which will have a size that's linear, n times d. The number of nodes and edges is near linear. So d is log n, so ignore d. And we're going to make a set of updates and queries to this graph that is not too big. It's only linear number of updates and queries. Mm-hmm.
Is the source a fixed vertex?
Sorry?
Is the source fixed?
Yes, let's say the source is a fixed vertex. Yeah, you cannot change the source. So the query is really like, just telling you, give me the answer. It's not just telling you what is the source or anything. Just, yeah. So we're going to create a graph, and we're going to change it. There's a sequence of updates, but the sequence of updates is small, only linear. And then with these parameters, we would be done. If we do this and we figure out the answer to OV, then we're done, because then if we had a sublinear time algorithm for the updates and queries, then you do sublinear times linear, you get subquadratic for all of them. And then you solve OV in subquadratic time. Okay. So do you want to suggest how it's going to look like? So like a hint, we're going to look at the graph OV. It's a graph problem. So like it's going to be like a reduction that kind of looks like the graph OV graph. Another hint, it's a bit similar to the exercise you had today with the single source max flow. Okay, anyway, it's late, so I'm not going to torture you. So here's what we're going to do. So the idea is like we're going to take this graph, and we're trying to create this graph, but we will do it somehow dynamically. So like, we will remove one part of the graph and replace it with just a source. And then we'll connect the source to the middle layer so that it represents one vector. And then we'll like ask a query. Then we will want to move on to the next vector. So we'll just delete the edges and add new edges. So it's like that. The right part will be there all the time, but the left part will is going to represent one vector at a time. So here's how the graph looks like. We have the source, we have the coordinate nodes, and the vector node, the B vectors. And yeah, the edges are defined exactly like before. It's just, if the coordinate is 1, you put an edge to the jth coordinate node. And as I said, this part will be static. It will not change. It will encode all of the set B. But then that part will be changing. It will encode one vector at a time. So here's the reduction. You go through the nodes in A one by one. You have a node, a vector. You have like a phase in the process. And this phase, you add the right edges. You add the edges so that the neighborhood encodes the vector. So you look at your current vector, you check for each coordinate, is it 0 or 1, and then you put an edge or not put an edge. Okay, after you do this, you ask how many nodes can S reach? And what is the answer? So if S can reach some vector B, some node vector B, then it means that there's a 2-path. And then it's not orthogonal to that B. The vector A that's being represented is not orthogonal to the B. So if there's no orthogonal pair, then you expect S to reach everybody on the right. So that's the observation. And then if S cannot reach a node B, then it means that A was orthogonal to that B. So the number you expect to see is like exactly n from the B, and then you also reach some nodes in the middle layer, but you know exactly how many. Like it's just the number of neighbors you have. So if you notice that you get the answer is smaller than this, then you know that okay, there's some B that I cannot reach. There's an orthogonal pair. Okay, so you do this. If you found an orthogonal pair, you're done. Otherwise, you want to go on to the next vector A. So you just delete the blue edges, and then you continue. So that's it. That's the reduction. It's correct. The efficiency is as I claimed, because, well, we have n stages, one for every vector. In each stage, we're doing just just D updates. Just the blue edges. There's D nodes in the middle, so it's just polylog n updates. Polylog n, we add polylog n edges, we make one query, we delete polylog n edges. Okay, so that was the lower bound. And in the beginning, I said we care about the pre-processing time. So what about the pre-processing time in this lower bound? The graph size was like n. So if the pre-processing is subquadratic, then great. Everything was subquadratic and fine. Now I'm claiming that we can actually prove a lower bound that holds even if the pre-processing is any polynomial. So even if the pre-processing time is n to the 100, this lower bound will hold. Start with the empty graph, but I'm not allowing you to add nodes. Yeah, if you could start with the empty graph.
No, as in empty, as in nodes are there, but there are no edges.
Okay, but right, we had n nodes.
Why would you do pre-processing if there are no edges?
Yeah, I don't know.
You just solve n to the 100 instances.
Yeah, how? What do you mean?
Like you just keep solving more instances. Using the same graph, and then eventually you solve instances.
Yeah, yes. So yeah, that's the right idea. So it's like I would like that. Okay, so like in this graph, right? This is the graph. So if I spend n to the 100, like pre-processing it, if like then I'm gonna make a lot of these updates, like n to the 100 updates, then I don't care like that the pre-processing was so expensive. Yeah, so that's what we want. And then luckily, we have this lemma. So ideally, we would like a version of OV in which the size of A is much, much larger than the size of B. Like n, if the size of B is n, the size of A is n to the 100. And we want to assume that this is hard. So if A has size n to the A, B has size n to the B, the trivial algorithm is A times B for every pair we check. So the trivial is n to the A plus B. And I want to claim that this is also a lower bound, assuming set. So why is that true? And this is like the general trick I was talking about before. Like this is useful in general to know that the set lower bound is not just like quadratic. It's really like parameterized by the sizes of the two sets. Yeah, exactly. So yeah, so it's like you know, if you have n and n, right? This is the standard thing. Here you need n squared, and I want you to get that kind of lower bound. Let's say A and B are less than 1. Otherwise, you can just do it otherwise. So you take you like partition it into blocks of size n to the B, and here you partition it into set blocks of size n to the A. And you use that kind of algorithm to solve those all pairs of blocks. And the number of blocks you have is n to the 1 minus A times n to the 1 minus B. That's the number of pairs. So if you could solve each pair in a time that's faster, then you get subquadratic. So it's kind of simple, yeah, but pretty powerful because then once we have this, then we can get the preprocessing. We just set like as you said, like we make A much larger than B, and then we preprocess this graph. N to the 100 is fine. It's just 1 over 100 to the 100. And then and the lower bound we have is weaker, like n to the 1 over 100, but that's fine. That's exactly the size of the graph, so it's still like a linear lower bound.
Just out of curiosity, can you also refer to this using the same reduction of Ryan-Williams, where instead of like splitting the variables down the middle?
Exactly. Yeah. So you could have proven this directly from SAT. By, you had in SAT, right, we had the n variables, we split them in half. Now split them however you want, like 1 over 10 and 9/10. And then you would get two sets that are unbalanced. One is much larger, and beating brute force is going to beat brute force in SAT.
Can you not use like some sort of like direct sum argument and say like k copies of like OB problem and take k times?
Yeah, so great. Like, just saying like direct sum and proving it like for any problem, I don't know. But luckily for OV, it's true because of this.
But is there like a more general form of this?
It's like, no, but if a problem has like a tight self-reduction, then it would hold. And many of the problems we work with have it, not all of them. Okay, so that's this result. Okay, so far we showed that these problems, like the reachability, we showed that it's hard, assuming set. Strongly connected components, you just add a bit more gadgets and you get similar hardness. Now I want to talk about diameter a little bit. So I said, okay, it's not easy. You need some, you cannot do polylog because then you'd get linear. But now I'm going to show you like an even higher lower bound. So here we showed like a linear lower bound, and here I'm going to show you a quadratic lower bound for diameter. It's very high because it says that every time there's an update, you have to run your quadratic time diameter algorithm from scratch. So it's like showing that it's a very non-dynamic friendly problem. Okay, so yeah, we have a graph. It's getting updated, and there's a query that asks for the diameter. And in n squared updates, you can compute APSP in a dynamic graph. So you can, of course, compute the diameter, but it's not any easier than that. So we're going to show that computing the diameter of a sparse graph, you need like quadratic time. And there will be another like nice trick here for Seth. And okay, so here's the trick. So instead of starting from OV, like on 2 sets, we're going to start from 3 OV. So instead of looking for a pair, we're going to look for a triple. So we have 3 sets of vectors of size n. And the question is there a triple that is orthogonal? And what that means is like if you put them on top of each other, there is no coordinate where they're all 1. And so I'm claiming that the complexity of this problem is n cubed. So why? We were going to put it on the exercise, but we forgot. So. Exactly, yeah. So it's the same proof for 2OV, except you split the variables into 3, not 2. Then you enumerate the alphas, the betas, and the gammas. Now there's 2 to the n over 3 of them, not 2 to the n over 2. So now you have like cubic time. Like beating cubic, you beat 2 to the n. And then you define them in exactly the same way. You put a 1 if they don't, you put a 0 if they satisfy, and 1 if they don't. And this check is really the same as just checking that you satisfy all the clauses. So it's the same proof. There is no reduction from 2OV to 3OV, no. There is a reduction from 3OV to 2OV. Do you see how? Sorry? Couldn't get it. Oh, this is, yeah, from 2 to 3, but this is not a tight reduction, yes. So if, no, but, so a tight reduction showing that if you break the, let's say you get this running time. Okay, Seth is false, fine. But do you also refute the 2OV conjecture? Do you also get subquadratic for OV? This we don't know. But what I'm saying is, if you get 2OV in subquadratic time, then you get subcubic for 3OV.
Can you do like every pair of 2 columns, and so you run 2OV 3 times, and then you do the classic decision to search constants to find whether they overlap, so that the orthogonal vectors are like AB and BC and AC.
That sounds like it would solve the problem in quadratic time.
Oh, I see. Okay.
I don't see it. Like you can blow up like to get that reduction, you can generate more vectors. So like
you can pick one vector on the third column, apply it to everything in the second one, and then solve 2 of it.
yeah.
For each other.
Yeah, exactly. Okay, yeah, that works. Right. So it's not what I had in mind, but it worked. So you take one vector at a time from the third set. You somehow intersect it with everybody on the first 2 lists, and then you would solve 2OV. And then you do this for every vector. So if you solve 2OV in subquadratic time, you get subcubic. Okay, anyway, so we have this cubic lower bound for 3OV. Now we're going to reduce it to dynamic diameter. Again, the graph will have linear size, ND. And again, we'll only have ND updates. But it's a harder problem. It's not just reachability, it's diameter. So we will have higher, we will be able to implement 3OV, not 2OV. Yeah, but, right, so it's the same as before, but the lower bound there is higher, so we get a higher lower bound for diameter. And so here's how the graph is going to look like now. It's kind of like the graph OV thing, but the middle layer got split into 2.
Why are we using the amortized time?
Sorry?
Rather than the worst case time?
Amortized? Why amortized?
Yeah.
It's just a stronger lower bound to say that even amortized, you cannot do it. The reason our lower bounds hold for amortized is because, well, I'm giving you a sequence of n updates, and the whole sequence needs to take quadratic time, or cubic in this case. Then what it means is that on the amortized, So the amortized is like the total time divided by the length of the sequence. So the amortized time needs to be linear or quadratic. Yeah. Okay, so that's the graph. So now these two parts will be static, and they will encode A and B. And what will be changing is this like middle layer, and it will dynamically encode C. So we look at C one vector at a time and change what's happening there. So here's how it looks. For every vector in C, we have a stage. And we look at the vector, and for every coordinate, either we put an edge or not. So it's like going to be like a matching between these coordinate vectors, these coordinate nodes. And it will represent the vector. It's like, like you want to find the path from A to B, but some of the nodes you're not allowed to use because like I didn't put an edge. And yeah, the observation is that like in this stage, the distance from A to B is equal to 3 if and only if A, B, and C are not orthogonal. Like the two-path proves that there was a coordinate in which all three were 1. That's it for the diameter thing. Now, so let's look at other problems that were on the list. Now, instead of single source or diameter, let's look at single pair. Let's say it's just ST reachability. The same kinds of lower bounds will not work. It's like we had a source and we asked a question and we found out something about all the targets. If the query is only asking about a pair, it seems like we need to ask a lot of questions. So Seth doesn't give us any lower bounds. Do you see a different starting point that would give us something? Let's say ST shortest path, weighted graphs. So it's like what we talked yesterday, kind of setting. So like, for example, if you have APSP, so here's like a nice trick. Like you want to know APSP, so you put some source and some target, and then you just you want to find out the distance for this pair, so you connect S to this and T to this, and you ask a query, and it kind of tells you the distance here. That's just like a hint.
Yeah, so then you can just use like the APSP, like you could update S like edges for SMT, and then you could update this.
Yeah. So you could just do this, and you get some lower bound from APSP. But you can do what we did yesterday and go from APSP to problems where you have like less pairs that you have to ask, and then you get an even higher lower bound. So for example, because of the n pair problem, you can get like a quadratic lower bound because you only have to do this like n times, and but the lower bound is cubic. So every time you do this, you have to spend quadratic time. So it's kind of cool. Okay, so that's just for weighted problems. Now what about unweighted problems? So if you remember from Nick's talk yesterday, we had like, he started with the unweighted problems, like triangles and the transitive closure and the BMM, Boolean matrix multiplication. And then he went on to the negative triangle and the APSP and so on. So here, if you take like the same kind of reductions, but you remove the weights, everything is going to work. So you do get a lower bound, let's say, of ST shortest path in unweighted graphs or ST reachability, which we wanted to talk about. But then you have to start with not APSP, but with like triangle detection or Boolean matrix multiplication and so on. And those problems were not cubic, they were subcubic, because we had this Strassen algorithm. But you know, if we could somehow assume that you need cubic time for those problems, then everything would work even for unweighted. And so on Friday, I'm going to talk about this concept of combinatorial lower bounds and algorithms, which says that, like, okay, you know, you solve this problem with this algebraic methods and so on, but we don't have a combinatorial algorithm for them yet. So until we have them, we have some combinatorial lower bounds here. I'm not going to go into it because it's not important for today. The reason is that there's this paper that said it's put this online matrix vector conjecture. And what it said is that when you do these reductions from like what I had in the previous slide, you go to these dynamic problems. What you're solving is not just like Boolean matrix multiplication, not just like triangle detection. You're solving it in an online way. It's like you're solving the problem matrix multiplication where like it's like a harder problem. It's online. So I'm not going to give you the two matrices. I'm giving you one matrix. And then the second matrix, I give you one column at a time. When I give you a column, like I give you this vi plus 1, you have to tell me immediately, you have to tell me the answer, the product with the matrix, before I tell you the next one. And what they said is that like this Strassen will not work here. The subcubic algorithms we have for multiplying Boolean matrices, they don't work when you have online. And the reason, if you remember, is like Strassen like splits each matrix into blocks and then find some clever thing to save on the multiplications and so on. But if you don't know the matrix, you cannot split it into blocks and use these cancellations and so on. So there's this conjecture that says that essentially like this, in the unweighted case, triangle detection, BMM, these things, in the dynamic thing, they're hard. And then if you use that, you get this lower bound, some lower bound for the ST reachability and so on. So yeah, that's all I want to say. It's nice that now we have like tight bounds for all these problems. Thanks.
So what do we know for approximate SSC and things like that in dynamic code? Lower bounds, upper bounds. The reduction fails that you gave for approximate.
For the number of things you can reach. Yeah. I'm not sure. I don't think they're hard, but I don't remember if there are algorithms also. Actually, I don't know. I think it's open.
I have a question about the dynamic code. I mean, 2 weeks step like the approach of making dividing the OB into 4 OB. I know it's wrong. Like if you do the same approach and then you do the
4 OB.
Yeah, 2 weeks step is wrong.
Yeah, it's. I mean, you could try, and it has been applied for other problems actually. Yes, but. Okay, so why doesn't it just work? Like just you put another layer and then you put the vectors and so on. Like, what's the problem there? So, I mean, I think just putting more layers will work. It's just that then you have to update both. Like for every pair, like C and D, you would have to. It gives you the same lower bound. Yeah, it's just gonna give you more updates. It's not. So I think what you're saying is like this. I put the A here, the B here, and then I put the gamma here and the delta here. Right? But then you have to try every gamma and delta. So the number of updates is just larger.
So the lower for is you and the form, yes?
Yeah, so it's more updates but a higher lower bound, but then it will just be the same.
Because you have to divide by n.
Yeah.
Computational geometry, there is some result that says, okay, if you use this much space, your data structure, then the best possible period time is related to the space you can use. So is that something that you can find in complexity is
So here we're focusing on the time, like preprocessing time and so on. These results are not talking about the space. The conjectures, they don't talk about the space. It makes sense to do it. It just hasn't been done yet.
What is known in the incremental setting in memory insertion? Because its reduction seemed to require additional setting.
Yeah, it's a good question. So there are some lower bounds. Some problems become easy in that setting, and so on. Yeah, you have to design a specific reduction for each problem. Like I think for like shortest path, you can do something. You know, like it's like you add, like you want to ask these n questions, so you keep adding. So in the incremental setting, you're only allowed to add edges but not delete edges, right? So you want to, let's say you want to ask like these questions one after the other, but you're not allowed to delete. So it's not like I add and then delete. So what I do is like I put some large weight here and then some smaller weight or something. So it's like I am adding more edges, but then when I add a new edge, it's like much cheaper than the previous one. And then it's like as if the previous one didn't count. So there are some tricks like that where you get lower bounds. There's another trick where you say, well, like in the previous reduction here, like we add some edges and we delete them. You can say, OK, I'm going to add edges, and then I'm going to like go back to the previous state of the algorithm. It's like I say, like I store the state of the algorithm in memory. I do some changes, and then I just go back to that state. And then it's like as if the edges were gone. This is like cheating. It proves a lower bound for worst case updates. It doesn't prove for amortized.
For the SSC, I think you just do insertion itself, right? The number of things you're connected to. Because you just subtract the previous answer each time you get the sum. And then you have a source, you connect to all the things in A.
Yeah.
And you just insert edge one at a time. So you add a fourth layer, which is your source.
No, but then you don't know if it's like what you're suggesting is like this, right? This is your source. You add this edge,
Right.
then you add this edge, and so on. But then you know when you added this, you could have reached like many of these.
Right.
When you add this, well, you already reached them because of the previous one.
So I don't- I need how many times or something? How many times I reach it, or how many different ways?
Right, then it's like max flow, and then this is like the solution to the exercise from today. The questions?
I'm still not getting why the reduction is going from one end to
Well, why is it? So at the end of the day, we get a worst case bound for like set or OV, right? But so suppose someone gave you a fast amortized algorithm. I mean, if someone gave you a fast worst case algorithm, like great, I'm happy. Every update, I'm going to make n updates. Every update is sublinear. So everything is subquadratic. But now let's say someone didn't give me a worst case algorithm. They only gave me a amortized algorithm. So only after a sequence of like n updates, the average time spent per update is sublinear. Just because of the fact that in the reduction, we are making this long sequence of updates. So,
we could have chosen the worst sequence.
sorry?
But we could have chosen the worst sequence of updates.
So what it means to be amortized sublinear is that for any sequence of updates, as long as it's long enough, then the average is sublinear. I mean, there doesn't exist a sequence that is like really bad in the sense that the average is not sublinear. Otherwise, it wouldn't be an amortized algorithm. So, I mean, even adversarially, you cannot generate such a thing. What you can do is like a small sequence of like log n updates, or then you can make those very expensive. But to amortize over a sequence of polynomial length, it should be fast. It's just a matter of the definition of the amortized. We can talk about it offline.
Many of these hardness of approximation, we are kind of getting it because the diameter can only be 3 or 4.
Yeah.
But there were some other results I think that were mentioned in which we had like stronger approximation cannot be done. Okay. So is there like does that go through some kind of finite PCPs or?
So tomorrow Nick will talk about it. So get some good sleep because.
Also, is there some like average case fine-grained hardness kind of stuff?
There are some things known, but very few, I would say. I might mention it on Friday. So on Friday, I will talk about like kind of a survey of what's happening in the field, and that's one of the things.
What about one-way functions?
One-way functions?
One-way functions.
So people are working on it, I would say.
Is the last lecture Friday morning or Friday afternoon?
No, just before lunch. Okay. Thanks.
2 more days for your fine.